Imagine taking a clean photograph and slowly sprinkling static onto it, frame by frame, until after 1,000 steps nothing remains but pure television snow. Now imagine training a neural network to run that movie in reverse, starting from random noise and gradually sculpting it back into a coherent image. That, in essence, is the idea behind Denoising Diffusion Probabilistic Models. And this paper from Jonathan Ho, Ajay Jain, and Peter Abbeel at Berkeley is the work that took that idea from a theoretical curiosity into a generative modeling powerhouse that rivals the best generative adversarial networks of its time. The motivation is straightforward. By 2020, the landscape of deep generative models was dominated by a handful of paradigms. Generative adversarial networks, or GANs, produced stunning images but were notoriously unstable to train and didn't give you a likelihood. Variational autoencoders, or VAEs, gave you likelihoods but tended to produce blurry samples. Autoregressive models like Pixel CNN generated pixels one at a time and were painfully slow at high resolution. Normalizing flows required carefully designed invertible architectures. Diffusion probabilistic models had been proposed years earlier by Sol Dickstein and colleagues, inspired by ideas from non-equilibrium thermodynamics, but they had never produced samples that could compete with the state-of-the-art. The authors here show that with the right parameterization and the right training objective, diffusion models can not only compete, but actually surpass leading approaches on standard image benchmarks. Let me explain how the framework works conceptually before we get into the design choices. There are two processes. The forward process, which is fixed and has no learnable parameters, takes a clean image and progressively adds small amounts of Gaussian noise over many time steps governed by a variance schedule. Crucially, because each step adds Gaussian noise, you can write down in closed form the distribution of the noised image at any time step given the original, which means you can jump directly to step 500 without simulating the intermediate steps. The reverse process is what we learn. It's another Markov chain, but going backwards where a neural network learns to predict how to slightly denoise the image at each step. If the noise added at each forward step is small enough, the reverse step can also be modeled as a Gaussian, which keeps the math tractable. Training proceeds via the standard variational lower bound on log likelihood, which decomposes neatly into a sum of Kullback-Leibler divergences, comparing the learned reverse transitions against the true forward posteriors conditioned on the original clean image. Because everything is Gaussian, these divergences have closed-form expressions, which means you avoid the high-variance Monte Carlo estimates that plague many latent variable models. Now here's where the paper's key insight comes in, and it's beautiful. When you stare at the term in the variational bound that compares the learned reverse step against the true posterior, you realize that what the network really needs to do at each time step is figure out what noise was added to produce the current noisy image. So instead of having the network predict the mean of the reverse Gaussian directly, the authors reparameterize it to predict the noise itself. The network looks at a noisy image and a time step and outputs its best guess of what random noise vector was injected. The loss then becomes simply the mean squared error between the true noise and the predicted noise, averaged over random time steps and random noise samples. Think of it like a detective shown a smudged photograph and asked not to reconstruct the original, but to identify exactly which smudges were added, because once you know the smudges, undoing them is trivial arithmetic. This reparameterization unlocks a striking connection. The resulting training objective is essentially identical to denoising score matching across multiple noise scales, which is the technique that Song and Ehrman had been developing in parallel. And the sampling procedure, which iteratively subtracts predicted noise and adds a bit of fresh noise back in, looks exactly like annealed Langevin dynamics. a sampling method from statistical physics where you follow the gradient of the data density while gradually cooling down the temperature. So a model trained with a variational bound on likelihood ends up, through this parameterization, learning something equivalent to estimating the score function of the data distribution at every noise level. Two seemingly different lineages of generative modeling turn out to be the same thing viewed from different angles. The authors also introduce a simplified training objective that drops the weighting factors that naturally fall out of the variational bound, treating every time step equally in the mean squared error loss. This downweights the easy denoising tasks at small noise levels and emphasizes the harder denoising at large noise levels, which empirically gives better sample quality, even though it makes the likelihood slightly worse. A few other design choices matter. The reverse process variances are fixed to time-dependent constants rather than learned, because learning them turned out to be unstable. The architecture is a U-net with self-attention at the 16 by 16 resolution and sinusoidal position embeddings to tell the network which time step it's processing. And the final step from the slightly noisy image to discrete pixel values uses a discretized Gaussian decoder so that the variational bound corresponds to an actual lossless code length. The results were striking. On unconditional CIFAR 10, they achieved an inception score of 9.46 and a Frechet inception distance of 3.17, beating every prior unconditional model and even most class conditional ones. On 256 by 256 LSUN bedrooms and churches, they matched progressive GAN quality. The ablation table is particularly illuminating. Predicting the noise with the simplified objective gives an FID of 3.107, while predicting the posterior mean directly with the same simplified objective fails to train at all. The combination of noise prediction and the reweighted objective is what makes everything click. There's also a fascinating analysis of what the model is doing in terms of compression. The lossless code length comes out to about 3.75 bits per dimension on CIFAR 10, which is worse than the best autoregressive likelihood models. But when the authors decompose this into rate and distortion, they find that more than half the bits are spent describing imperceptible details, while the perceptually meaningful content is captured in the first chunk of bits transmitted. The sampling process behaves like progressive decoding, where large-scale structure appears first and fine details emerge later. They even draw a formal connection showing that a particular degenerate version of the diffusion framework reduces to autoregressive generation, but with a generalized notion of bit ordering that doesn't correspond to any spatial scan over pixels. Now for the limitations. Sampling is slow because you need 1,000 forward passes through the network to generate a single image, which makes diffusion models far more expensive at inference time than GANs or VAEs. The log likelihoods, while reasonable, aren't competitive with dedicated likelihood models like sparse transformers. The simplified objective that gives the best sample quality is no longer a proper variational bound, which means you're optimizing something slightly disconnected from likelihood. And the authors acknowledge that learning the reverse process variances proved unstable, leaving a degree of freedom that future work would need to revisit. Now let's walk through some questions you might have after hearing all of this. Why does predicting the noise work so much better than predicting the clean image or the posterior mean directly? The intuition is that at every noise level, the network is being asked to do a task of roughly comparable difficulty, namely identifying a Gaussian noise vector, rather than tasks of wildly varying difficulty like reconstructing a clean image from almost pure noise versus from almost clean input. This normalizes the learning signal across time steps and pairs naturally with a mean squared error loss. It also makes the connection to score matching explicit, since predicting the noise is essentially predicting the gradient of the log density at that noise scale. Why do you need 1,000 time steps? And could you get away with fewer? The number of steps matters because the math relies on each forward step adding only a small amount of noise so that the reverse step can be well approximated by a Gaussian. If you took bigger jumps, the true reverse distribution would become multimodal and a single Gaussian wouldn't suffice. 1,000 steps is a hyperparameter chosen to keep each step small while giving the model enough total capacity to transform pure noise into images. Subsequent work has shown you can sample with far fewer steps using cleverer solvers. But in this paper, the long chain is what makes the simple Gaussian reverse model work. How is this fundamentally different from a variational autoencoder, since both have latent variables and a variational bound? The crucial difference is that in a VAE, the encoder is learned and tries to find an informative compressed latent. In a diffusion model, the encoder is the fixed forward noising process, which has no parameters and pushes the final latent toward pure Gaussian noise with essentially zero mutual information with the data. All the modeling capacity goes into the reverse process, which is a deep chain of denoising steps rather than a single decoder. This separation is what allows diffusion models to avoid the posterior collapse and blurriness issues that plague VAEs. Now thinking about how this connects to large-scale recommendation systems, the most immediate application is in generative retrieval and synthetic user modeling. Diffusion models excel at capturing complex, multimodal distributions, which is exactly what you face when modeling user behavior, where a single user might plausibly engage with very different items depending on context. You could imagine training a diffusion model over user embedding trajectories or session sequences, generating diverse candidate sets by sampling from the reverse process, and using the progressive structure to first commit to coarse intent and then refine towards specific items. The progressive decoding property is particularly interesting for candidate retrieval, since you could truncate sampling early to get a fast, low-resolution candidate set and then refine only the promising ones. The bigger practical concern is the 1,000-step inference cost, which is a non-starter for real-time ranking at billion-user scale. But the same noise prediction framework underlies modern fast samplers and distillation techniques that can compress a diffusion model into a handful of steps or even a single forward pass, which would make it viable. The conceptual gift to recommender systems is that variational inference and score-based generation are the same problem in disguise, which means tools and tricks from one community immediately become available to the other for tasks like learning over sparse interaction matrices or generating counterfactual user trajectories for off-policy evaluation.